Alright, so let me start today's lecture, and today we're gonna start a new course focusing on the motions of the molecules in liquid and how the motions of the motions of the molecules in liquid is related to the viscosity and dispersion, and focusing on the movement of the ions. So before starting today's lecture, let me talk about the plans on our course, Physical Chemistry 2, for the next couple of classes. So we have a Chuseok holidays in this week. So I decided to provide the class number 5, this class, and the class number 8, which is the after course in the recorded format, just to help you to follow the course materials. So I basically believe that it's more effective to have classes in the classrooms physically. So I'd like to place more important lectures to have in classroom, which is the classes number 6 and 7. So we're going to do 6 and 7 in the class, and the number 5 and number 8 will be provided in this recorded format. And then the first homework will be uploaded on 19th day of the September on ETL. You're going to have 2 weeks to solve for the problems in the problem sets and first problem set. So this is today's lecture contents. We're going to talk about new topic, which is motions in liquid. It is corresponding to topic 16B, belongs to focus 16 of the Atkins textbook 11th edition. So basically, the numbering of the chapter may depend on the edition you have. So today we're going to talk about the experimental result for the motions in liquid, so viscosity, and we're going to talk about the electrolyte. And then we more focus on the mobility of ions in the liquid phase, focusing on drip speed, mobility, and conductivity of liquid phase. And finally, we are going to reach the Einstein relation. So in the last lecture, we had discussed the relation between kinetic molecular theory and the transport properties like the diffusivity and thermal conductivity and viscosity. And we drive the relation between the viscosity and the mean speed and mean free path and the number density and kind of that, and we could find out the direct relation based on the kinetic molecular theory between the diffusivity and thermal conductivity and viscosity and the thermodynamic properties like the temperature and pressure and which is the intrinsic property of the molecule, which is the molecular weight, so that may be able to find out the direct relation between how the transport properties depends on gases. It depends on the temperature and pressure and molecular weights like this. And also we also discussed about the effusion based on the Graham's law of effusion, and we went through one example about the partial pressure of the very heavy very heavy atom, which is the cesium, right? So today we are going to talk about the motions in liquid. So basically, the environment of the molecules within the liquid phase is very different from the case of the gas phase, you know. So there's some techniques to analyze the molecular or ionic dynamics in the liquid phase. So basically you see here that if you mix the ink with water, and the ink molecules will diffuse into the water, and also it is related to very important applications like the drug delivery kind of that. So if you have pills and pill, then these drug pill will be dissolved into the molecules have the pharmaceutical activity within your intestine organs, it's like this. So it is very important to understand the transport property in the liquid phase. So let me tell you briefly about the techniques to analyze the liquid motions. So first thing is the nuclear magnetic resonance. So I'm pretty sure that you might have known that the NMR is the technique to analyze the structure of the organic molecules, probably from the organic chemistry, but it is the NMR has a very strong physics background and also can be used to analyze the motions in liquid. So based on their intensity, so kind of that. So basically, you can measure the relaxation times or various types of the properties of the molecule that is related to the molecular motions in the liquid phase. And then also you can use the inelastic neutron scattering. In short, we call it INS technique. So neutron may collide the molecules or ions in the liquid phase, and they may lose or gain energies because their scattering or collision is inelastic. So based on the changes in energy, we can find out some basic facts about the molecules' motions in the liquid. So I'm not going to talk about any details about this technique in this class, but I think it is pretty good to know to have these kind of techniques are useful to analyze the motions of the molecules in liquid phase. And third one is the direct measurement of the viscosity. So we actually went up through one example that we can correlate the torque and the viscosity of uh, the fluid, as we discussed in the previous lecture, one of the examples. So we can use in the lab, we can use some kind of viscometer like this, which is called the co-ed viscometer. And it is composed of a bob, which is just column-like thing in here. And we have a cup here. So it is some kind of container here. So have the bob and cup have the radius of kappa r and r. Here the kappa is the some dimensionless parameter having values from 0 to 1. So basically the radius of the bob is smaller, slightly smaller than the radius of the cup. So you fill the rest of the space after you're putting the bob inside the cup, and you rotate it and develop the velocity gradient between the cup and the bob, and then maybe able to read the value of the torque to which is required to rotate this bob with at some certain the um, angular velocity, so that you can find out the viscosity information of the liquid sample that you put inside this cup. So this is one of the simplest viscometer you can use in the lab. And then the topic that we are going to talk about today is related to electrophoresis. So basically, it is about the movements of the ions in the liquid phase. So if there is some kind of the potential difference, let's say this large V, then there should be some kind of electric field within this liquid phase. It is exerted in the sample. Then some ions in positive and negative will be dragged by the electrostatic force. And just by measuring and you move some charge, that means you have the electric current, then you may be able to find out some kind of the resistance or the conductance of this liquid sample, so that you can correlate those kind of liquid conductance to the intrinsic properties of the liquid phase that is related to the motions of the molecule in the liquid phase. So that this is the topic that we are going to talk about today. So let me tell you about the liquid viscosity, and we have seen this the phenomenological equation, which is called the fixed force law here. This is true both for the gas and liquid phase, as long as the fluid follows the Newtonian behavior. So the fluid types of the fluids that follows this relation is called Newtonian fluid, and most of the gas and liquid belongs to this Newtonian fluid unless they have. Also, we have some kind of special types of the fluid, such as the molten polymer, that kind of that. Those kind of liquids doesn't follow this this Newton's law of viscosity, and so this basically this equation can be applied to the to correlate the momentum flux and the velocity gradient, and as well as the momentum flux, the physical interpretation, one of the physical interpretation of the momentum flux, the shear stress, and the velocity gradient can be understood as the rate of the deformation. So the viscosity is the property of the liquid that correlates the shear stress and rate of the deformation. So let's think about these two cases. So we have the liquid 1 and liquid 2. And here the same shear stress was given. So but the different velocity gradient was developed. So we have the high velocity and low velocity from the bottom plate and top plate. And here the low velocity here is according to the no slip condition. So we have stationary top plate. So at z equals L in both liquid, the liquid velocity is 0, but due to the difference in the viscosity, even though you apply the same shear stress, velocity gradient steepness is different. In this case, the viscosity of the second liquid is higher than the first liquid. So if the shear force per area, which is the shear stress, are the same for both cases, then rate of deformation should be larger in the first case. So which means that the liquid 1 is less viscous than the second liquid. So basically, you can think that small viscosity allows the liquid to flow faster, which means to have the greater rate of deformation or velocity gradient. So I think we have seen these moving pictures in the comparing the water and engine oil and honey. So three different liquids are under similar shear stress because the similar shear stress because all of them are under the same gravity, and the densities of these liquids are not so different. So basically, the gravitational force which generates the shear stress on this liquid bodies are not really different, but due to the difference in the viscosity, the rate of deformation is very different. So you see the water moves very quickly, but while the honey having very high viscosity compared to the water or engine oil moves very faster. Much sluggish, slower than the two cases. So this is the demonstration for the liquid viscosity, and so it's unlike the case of the gas. So inside the liquid, so in the perfect gas molecule, we basically assume there's almost no interaction among the molecules inside the phase. So let's think about the energy when traveling the space. So in gas phase, unless they have some kind of collisions, the gas basically feels no barrier in translation, so that we have almost no energy barrier in this curve. But liquid is pretty different. So inside the liquid, there is huge number of the intermolecular interactions, unlike the case of the gas. So for molecule to go through this liquid phase, and they should overcome some kind of energetical barriers that is generated by the surrounding molecules. So this is the main difference between the liquid phase and gas phase here. So for liquid phase, still the molecules follows the classical mechanics. So probability to escape this potential wall is the same as probability to have energy higher than this activation energy, which is the energetic barrier for movement. And this may follow the Boltzmann distribution. So this is the probability for molecule to have the energy higher and the same as this this energy barrier. So basically it follows the Boltzmann um, thermodynamics. And the next thing we have to think about is the Hoping frequency. So the molecules basically tries to overcome this barrier, and there should be some kind of frequency defined as the number of the trials per the unit time. So this Hoping frequency will be proportional to the rate of deformation. So if this molecule tries to overcome this barrier more frequently within the unit time, then that liquid will have the high rate of deformation, which is proportional to the Boltzmann distribution given here. So the higher popping frequency is, then the more mobile molecules are, which means that there should be less viscosity of the liquid is. So the 1 over rate of deformation, should be inversely proportional to the viscosity according to the Newton's law of viscosity, and it should be proportional to now exponential of plus EA over RT. And if you write down in the Boltzmann form, then the viscosity will be proportional to this value, this factor, and this mu, and this is the some viscosity coefficient here. So viscosity may follow this Arrhenius-like equation. Not really similar, but the Arrhenius equation has the pretty similar format. Okay, so basically viscosity is related to how momentum is transported. So within the liquid phase, for molecule to go through this liquid phase, then that molecule must overcome some energy barrier casted by the surrounding molecule. So if the molecule moves faster, then which means that molecule can be escaped from some kind of energy well or energetically trapped by surrounding molecule. If it is convenient, then the liquid may have lower viscosity, but the situation is pretty different from the gas phase. So basically in the gas phase there is no intermolecular interaction, and the momentum is basically carried by the movement of the gas molecules itself. So it basically depends on the collision. So we have discussed this picture. We have the x-axis here, reduced temperature, basically temperature, and the y-axis is the viscosity. So for liquid phase, if you increase the temperature, then you will make all the molecules easier to move, and then you have the less viscosity as you increase the temperature. But for the gas phase, then if you increase the temperature, the collision frequency will increase. Then the momentum transport becomes more and more effective as you increase the temperature. As a result, the viscosity goes up. So that's the main difference between the liquid phase and the gas phase. So let's go through one simple example. So we have the viscosity of water that was measured at room temperature 25 degrees C and 50 degrees C. So we have two values of the viscosity of the water. So in the room temperature, the viscosity of water is nearly in the order of 1 centipoise. So the measured value here is 0.89 centipoise. And at higher temperature, 50 degrees C, we measure the less viscosity of the water, which is 0.547 centipoise. So here, with these two temperatures, just like the case of the Arrhenius equation that we have studied in the general chemistry, we can calculate the activation energy that is required to migrate for water molecule to go through the liquid water phase. So here we have the equation with dependency of the viscosity of the liquid phase, molecules in liquid based on the Boltzmann distribution here. And we have the viscosity values at the two different temperatures here, T1 and T2. Then basically we assume the activation energy is not the function of the temperature. Then we have these two equations, and then we divide the second equation by the first equation. We can neglect this eta zero term, and finally we have the relation between the ratio of the viscosity and difference between inverse of the temperature, so that we can find out the value of the epsilon. So if you solve for, sorry, not EA, so if you solve for this equation for this EA, then you have this equation and you have the two viscosities and two different temperatures. Then you can find out the activation energy required to migrate for a water molecule to go through the its own water liquid phase. So it is can be calculated as 1.56 times 10 to the 4 joule per mole. So, but this activation energy is pretty close to the strength of the hydrogen bond. So, which means that for a water molecule to go through the liquid phase of the water, then it must have overcome some kind of energy barrier. But it is the energy barrier, the scale is exactly at the same scale of the hydrogen bonding energy. So we can find out why the water is more viscous when compared to the other types of the molecule. So you see, if you have some kind of previous experience to deal with some kind of light organic solvents like the acetone or some other things like the hexane, they are less viscous than the water because they don't have any hydrogen bonding among their molecules, but water has the hydrogen bonding among their molecules, so that it will have stronger the activation energy, so that it has a higher viscosity when compared to some other. Okay, so let's move on our topic to the electrolyte solution. So now we have the system, we have the liquid phase, and we have some ions. So it is some kind of liquid solution of some salt. So can be ionized inside the liquid phase. So if you apply some kind of voltage difference on this liquid phase, then the cations and anions will move in opposite directions like this, and as a result of movement of this ion, you will have some kind of current, so that you have the voltage difference and you have specific values of the current. Then there should be some kind of ohmic relation. So here's the equivalent circuit. So now you apply some voltage on this resistance here R, which is corresponding to this liquid phase, and as a result you have some kind of ionic motions in liquid phase, which is corresponding to this current. So bulk of solution basically has some kind of property which is corresponding to the electric resistance. Here is denoted as large R, but here is basically more convenient to use the inverse of the resistance R, which is defined as conductance. Here it is denoted as large G. So the unit of the G is the inverse of ohm, or which is defined as Siemens here. It's also the spin-off of the SI unit system. So here the relation between the voltage difference and the amount of current has this proportionality relation that you know as the Ohm's law, and also in terms of the conductance, you can write the same Ohm's law as V equals to I divided by the conductance. So here the higher conductance is, which means that you have the better conductivity when you have the same values of the voltage difference, then you have the more ions transported within a unit time. So basically, conductance is some kind of innate property of this liquid sample that is hooked up to this voltage difference here. So conductance G may depend on the dimension of this bulk of the liquid solution here. So conductance G, you will have more conductance. You have the larger area, which is the large A is the cross-sectional area of the liquid sample here, and will be inversely proportional to the length of the sample. So if you elongate this the liquid phase, then you may have larger resistance. Then it is pretty obvious that the value of the G will be inversely proportional to the length of the sample. As a result, you have some kind of the proportionality coefficient here, which is called electrical conductivity. So here the kappa of small e, as kappa is called the electrical conductivity, and unit of this electrical conductivity, as you hear, so this is the unit as Siemens, and you have this is the A over L has a dimension of just the length. As a result, the unit dimension of the electrical conductivity is inverse of the resistance and inverse of the length here. So as a unit system, it has the dimension of has the unit of Siemens per meter. And you see here the value of this one is no longer depending on the dimension. So it's but dimensions. So here the dimension is basically extensive properties of this solution bulk, and this kappa value depends on the innate inherent property of this solution sample, and it is an intensive property. So this innate property, which is the electrical conductivity, may have some relation to the property of the solution, such as the concentration. So if you have a higher concentration, then you have some more ions per unit volume. So as a result, you will imagine we're going to have higher electrical conductivity. So we're going to try to eliminate the effect of a concentration. So we define the molar conductivity, which is written as large lambda m, and we divided the electrical conductivity by the concentration of the solution. Then you can replace this kappa value with the product of the molar conductivity and the concentration here. I'm sorry. So now you can see some kind of proportional relation here. The conductance of this liquid sample will be proportional to the cross-sectional area of this bulk and inversely proportional to the length and also proportional to the concentration. So here the global coefficient, which is molar conductivity, is large lambda m, can play a role as an indicator for the innate ion motions in the liquid. So let's talk about this a little bit more. So here the molar conductivity has the dimension unit of Siemens area per mole, and its typical value is within a range of 0.01 to 10 milli Siemens per it is about at this value 0.01 Siemens square meter per mole, kind of that. So now we obtain indicator, which is the molar conductivity ion motions of liquid. This is the molar conductivity, and we can ask us a question that does this value, this molar conductivity, purely a material property or not? In other words, we can test if this molar conductivity depends on the concentration of the molecule or not. But unfortunately, the answer is no. This molar conductivity still depends on the concentration. So it is a function of the concentration. So this means that the concentration of the electrolyte, which is the ion species, influences the motions of the liquid in liquid phase. So there are two reasons. So in case of the non-strong electrolytes, so the concept of the strong electrolytes means that if you mix the salt in the water or the liquid phase, if that salt dissolved 100%, then we call it strong electrolyte. So that if you have the non-strong electrolyte, so that if you mix the salt with the liquid, then not 100% of the liquid electrolyte is dissolved into ion species. Then if you double the nominal concentration, that it doesn't double the ionic concentration. So you can say that the this C is not purely proportional to the concentration of the ion inside the um, electrolyte solution. And also for if strong electrolyte, even though you have 100% dissociation, if the ions interact strongly, then the strong inter-ionic interaction will generate some kind of the nonlinear relation for the movement of the ions. So this value will still depend on the concentration. There's two reasons. So we may have some kind of empirical equation that correlates the molar conductivity and the concentration. And one of the famous equation is the Clausius law. So here we have some constant. So lambda 0 m, this is the constant, and we have the concentration dependent term here. So Clausius law describes the functional relation between the molar conductivity and the concentration at, this is important, at only at low concentration, so that the C should be lower than 0.01 mole per liter, and the electrolyte should be strong electrolyte, just like the salt NaCl, or the salts that has very high solubility, like this, like that. So only apply those kind of system. But still, the Clausius law describes the relation between the molar conductivity and the concentration pretty well. So it was developed by the Clausius, who is a German physicist in 19th century. So you may see some kind of question when you see this equation. So if you increase the concentration, then molar conductivity will eventually go below zero. If the value of this concentration dependent term is larger than this constant, then overall value should be negative. But that doesn't happen because this Clausius law only describes when C is very small. So we basically don't reach the high concentration region that can make this value negative. This C value is basically very small. So this is the system that is required by the Clausius law. Okay, so Clausius tells you that the molar conductivity of the strong electrolyte, when the concentration is very low, then it may depend on the square root of the concentration, like this. So here, the large lambda 0m is truly constant. It doesn't depend on the concentration, and we call this limiting molar conductivity. So if the concentration is very small, so if you can take a limit of C onto 0, then the overall conductivity, overall molar conductivity will approach the value of this limiting molar conductivity. So at zero concentration, then the ion is very scarcely distributed in the liquid phase. So inter-ionic distance must be very long when compared to the intermolecular distance in the liquid phase. So we can assume that ions will move independent from one another. So 100% of the surroundings, the particles of one ion should be the solvent molecules. There is no ion-ion interaction. So ions are totally free from the interionic interactions among them because the concentration is very low. Then this limiting molar conductivity is just an indicator for the ion-solvent molecule interaction because we can completely rule out the effect of the ion-ion interactions. So at zero concentration, so very, very low concentration, there is no interionic interaction. So the molecular conductivity can be written simply as the linear combination of the contribution of cation and anion. So there is no relation, no interaction between cation, anion, or cation, cation kind of that. So we can simply make a summation of this cation contribution on the limiting conductivity and the anion contribution to the limiting conductivity. Here, the small lambda plus minus is called the limiting molar ionic conductivity of cation and anion. And here nu is the number of cation or anion per chemical formula of the salt. For example, we have NaCl, then one NaCl will make one sodium cation and one chloride cation, so that the nu plus minus in that case, they are just 1. Okay, so let's see this example. So here we have the solution of the potassium chloride as room temperature, and the conductivity is given as 14.688 millisiemens per meter, and the concentration is also given. And at different concentration of the salt, the conductivity is also given. So if you increase the concentration 5 times and you have this value of the um, conductivity, and the question asks you to determine the value of the limiting molar conductivity from the Clausius law and the Clausius constant, the K here. So first step is evaluating the molar conductivity of the two concentrations, and here it can be obtained by dividing the conductivity, which is given here at two different concentrations, and if you divide with the nominal concentration, then you have the value of the molar conductivity at these two concentrations. As you can see here, the value is slightly different. So it means that the molar conductivity, if you increase the concentration, then you decrease somehow the molar conductivity like this. So you see that the molar conductivity also still depends on the concentration. And second thing you assume is that these molar conductivities may follow this Clausius law here. So now you have the two values of the molar conductivity at two different values of the concentration, so that you can solve for the two unknowns, which are the limiting molar conductivity and the Clausius constant here. So if you solve for that, then you can get the values of the two like this. So this is one of the very simple example where you can play with this the Clausius law. So let's move on a little bit about the mobilities of the ion in the liquid phase. So limiting molar conductivity basically characterizes the mobility property of ion, which is the free of the interionic interaction. And just we think of the interaction between that ions and surrounding solvent molecule. So what we are going to focus on is the drift speed. So drift speed is the nominal apparent speed that one ion species traveling inside this liquid phase. So let's think about a system. We have the bulk of liquid here, which is the solution of electrolyte here. There should be some kind of ion, and the length is L. And now we apply the voltage difference of delta phi here. Then you generate the electrical field here is denoted large E. So large E, it is, if you study the general physics, then the scale of the electric field E can be correlated to the potential difference and the length between the two plates, electrodes, which is the delta phi over L. At the same time, each ion has the charge, and for example, maybe plus one cation, plus two cation, kind of that, those kind of number of the charges is denoted here as the value of small z. So charge that is possessed by one ion is Q, which is the product of the Z and E. And here the electrostatic force that it exerted on this one of the ions here is the product of the Q and the magnitude of the electric field according to the general physics knowledge, which is QE here, and you substitute this Q with Z and E here. So the electrostatic force one ion experience inside the system equals to Z, E, and large E. So they will be dragged by this electrostatic force, but this liquid basically has some kind of viscosity. So there should be some kind of viscous drag force in opposite direction, so that at the equilibrium of the force, this ion will reach some kind of the constant velocity, which is basically drift velocity, drift speed, and at that situation, there should be equilibrium between the two forces here, the Ze multiplied by large E, which is the electrostatic force, and opposite side you have the viscous force, which is expressed as the product of friction factor and the drift speed. Small s is the drift speed, so viscous force is proportional to the drift speed, and proportionality coefficient is called friction factor here. So now we have the balance between the two forces, viscous drag force and the electrostatic force. So here the small f is called the friction factor, F. And according to the Stokes law, so if the value of F depends on the size and the shape of the object traveling inside the viscous media. So here the ion has a spherical having the dimension of small a here, size of small a here. Then we can use the Stokes law that correlates the friction factor and the viscosity and the size of the sphere inside here. This is the Stokes law. Then you can combine this to solving for the value of the friction factor here. So here the eta is the viscosity, and A is the called hydraulic radius, which is related to the size of this ion, effective size of this ion inside the liquid phase, or also we call it the Stokes radius. So if you take the equation of two expressions, then you can solve for the drift speed small s as the ZEE divided by small f here. So this result shows that this drift speed is proportional to the external electric field large E, and here the proportionality coefficient between S and E is called the mobility of this ion small u. So there is the direct proportionality relation between this drift speed and the extent of the size of this external electric field. The proportionality coefficient is called mobility of ion small u, but from this equation of the force, we can find out that small u is can be written as the ratio of the Ze, which is the charge possessed by one ion divided by the friction factor S. So ionic mobility U has this dimension. So let's see this example. So ionic mobility of the sodium ion in water is given that having this value, 5.19 times 10 to the minus 8 square meter per second, and volume. So if think about situation, you have a solution length of just 1 centimeter, and you apply the voltage difference of 1.5 volt, which is corresponding to just one common battery cell you can buy from some kind of convenience store, and you applied the voltage on the thickness of the liquid having 1 centimeter thickness, then you can calculate the magnitude of the external magnetic field, which is corresponding to 150 volt per meter. Then based on this relation, you have the value of the U, and you just calculate the value of the electrical field so that you can estimate the size of the drift speed of the in the liquid phase of the sodium ion, which is corresponding to 7.79 micrometer per second. So if you buy some battery and then you apply to that voltage of the 1 centimeter thickness salt concentration, then the sodium ion will move at this speed. So this is what the drift speed and the concept of the mobility of ion can tell you. So if you can combine the friction factor according to the Stokes law, then now you have the relation between the mobility of ion and the size, effective size of the ion inside this solution. So actually the size of A is the size of the hydration or solvation sphere. That's a topic that I'm going to talk about right now. So now we have this relation. And what we are going to do is we are going to compare the values of the ionic mobilities of the alkali ions and alkali group cations and the halide group anions here. So let's first look at the case of the alkali group elements. So here we have the proton and lithium, sodium, potassium, rubidium, and cesium. But as you increase the size of the ion, then if you increase the value of the A, then the mobility should go down. But you see some very strange behavior here. So if you increase the size of the ion itself, then the mobility goes together, increases higher, except for the case of the proton. So ionic mobility of proton is very high among all the ions. This is one of the expected thing, but the lithium ion should be second highest, but it is lowest. And cesium and rubidium should be lowest, but it has very high. It is very weird. And similar trend is also observed for these anions. So fluoride anion is smallest, so it may have the highest value, but has the smallest value when compared to other halide anions. So this is because the ionic mobility is primarily determined not by the sheer size of ions, but by the size of the hydration sphere, which is the effective size of the ion inside the water. So here we have the strontium cation inside the water, and due to the electric field that was made by this positive charge of this cation, all the water molecules are attracted to have some kind of disordered structure. And if you want to move this ion, then these group of water molecules move together. So this makes the effective size of this cation inside the water species. So we call this a group of water as a hydration shell, and the hydration radius is the radius of this hydration shell. So small ions like the lithium is actually more extensively solvated when compared to the large ions. So actually, the hydration shell radius of the small alkali ions like the lithium and sodium is actually larger than the hydration shell radius for the potassium and rubidium. So as a result, the small cations has lower the ionic mobility, and this is the same true for the halide anion case. But what about the protons? Protons smallest, and proton may have this kind of hydration sphere that may be most effective and may have the largest hydration shell, but that is not true because the movement to the proton is on totally different mechanism because the proton is just a part of the water molecule. So proton can be transported like this uh, by hopping among the water molecules. So this mechanism is called Grott's mechanism. So this is the mechanism, one example, one explanation for large value for the proton for having the ionic mobility. But if this proton movement happen along really this mechanism, it is still open to question. We don't know exactly, but this is one of the suggested mechanisms that tries to explain the highest ionic mobility for the proton. So let's get back to the relation between the mobility and the conductivity here. So now we have two quantities measure the intrinsic ionic mobility of the electrolyte solution. One is the limiting molecular conductivity, large lambda m, which is from the Clausius law. Okay, so this is what we have studied. And the second part of the previous part of this lecture, we also discussed about ionic mobility, small u, is related to the amount of charge and the radius, hydration radius here, according to the Stokes law. So rest of the lecture, we have make a correlation between limiting molar conductivity and ionic mobility here. So we are going to establish the direct relation between this limiting molar conductivity and the ionic mobility here. So we are going to consider a solution of electrolyte having the molar concentration of C. And each formula of the salt give nu plus cations of charge Z plus E and nu minus anions of Z minus E charge. So for example, we have the sodium sulfate. For this salt, for per one chemical formula, it will give two sodium cations. So nu plus is going to be 2 here, and a charge carried by single sodium ion is plus E. So here the Z plus is plus 1 and E is the charge of 1 electron here. And the same for the sulfate anion here. So every single Na2SO4 gives 1 sulfate anion. So we have the value of 1 for this nu minus, and each of the anion carries negative 2e charge. So Z of Z negative equals to negative 2 here. So the value of nu and Z are determined by the chemical formula of the salt, and the molar concentration of each type of ion can be written as the product of nu multiplied by C. So nu can be nu plus or nu minus here. So we are going to consider the system based on the number of ions. So we have the concentration. So if we have the size of the system and the volume, then we may be able to count the number of the ions just by multiplying the molar concentration of each type of ion we multiply the Avogadro number, then we can convert the mole number into just the sheer number. So now we have the number density, And we're going to consider this system. We have the bulk of the liquid, and we're going to think of imaginary window having the cross-sectional area of A, so that now the molecules, sorry, the ions will travel this liquid with the certain drift speed, so we can calculate the number of the um, ions that is going to pass this imaginary area A simply by obtaining the volume of this liquid by multiplying the length, which is the product of the drift speed, and for some delta t here. So if you multiply the number density with the volume of this, then this is the now you have the sheer number of the ions. You counted the ions inside this volume, and you have the relation between the number density and molar concentration like this. Now you have this expression. This is the number of the ions inside this volume. And then we are going to calculate the electric current induced by this ion flow. So each ion carries this amount of charge. So if you multiply the number by the charge, then you can calculate the total charge that passes through this area during delta t. So this is the number, and this is the charge per one ion. So now you have the total charge. And if you divide the charge with the time, then will be the electric current. So that's the thing that we are going to do. But if you focus on here, if you multiply the small e here, this is the charge carried by one electron. If you multiply the Avogadro number, then you find out this constant, which is the product of the unit charge and the Avogadro number, which is defined as farad. Farad is the charge carried by 1 mole of the electron, which is corresponding to roughly 96,000 coulomb per mole. So you can substitute the Avogadro number and E with the F, large F, having this value of the constant. Then you divide this charge value by delta T, then so that you have the electric current. So electric current is Z S large A nu CF. This is the current by drifting ions. So we're going to set the expression for the conductance and the conductivity and the small lambda value. So here, according to the Ohm's law, the conductivity can be written as the I divided by the potential difference, because it is the inverse of the resistance large R. So if you substitute this I value with this group of the parameters, so that you have the expression for large G, which is the conductance, and you go through this definition for electric conductivity. If you multiply the L, if you divide it by this value with A, which is the cross section, then you will get the electric conductivity, which should be Zs nu Cf L divided by the potential difference. So this is the electric conductivity you just got. And now if you divide the electric conductivity with the concentration, then you have the molar conductivity of the ion. So you drop the nu and c here. Now you have Z as large FL divided by delta phi. So here the concentration is very small, the Coulomb law is satisfied. So you can find out the molar conductivity of the ions and the parameters defining this electrolyte under the potential difference system. So here we introduce the ionic mobility that we have discussed previously, and there is the relation between the drift speed and the size of the electric field the proportionality coefficient is called ionic mobility small u. So it can be alternatively written as the ratio of S over large E, and large E is the ratio of the delta phi over L here. So here we have U equals to SL over delta phi. So if you look at this relation between lambda and the other parameter, then you can find out SL over delta phi. So you can substitute this part with small u. So as a result, you find out the direct relation between the molar conductivity and ionic um, conductivity between the small u here, ionic mobility, small u here, has the relation of lambda equals to z u large F. And this is true for the cation and anion. So we have briefly discussed about the large lambda m can be expressed in terms of the independently written as a sum of the contribution of cation and anion. So if you substitute small lambda plus and small lambda minus with the expression based on this ionic mobility, then you reach this relation. So large lambda m, which is the limiting molar conductivity, equals to the product of large F and the sum of nu Zu of ionic species that present inside the liquid phase. So we call this law as law of independent migration of ions, reflecting the assumption of there is no ionic interactions. All the ions move just independently without experiencing the interaction between ions. All the movements are governed by the ionic solvent surrounding sorbent molecule interactions. Okay, so let's move on to the last topic of today's lecture, which is the Einstein relation. So the last part of this lecture is about the relation, making a relation between the limiting molar conductivity and the ionic mobility and the diffusivity of ion. So diffusivity may come from the fixed fast law. So here that we are going to talk about this next class. So this we have the relation between the drift speed and the force experienced by 1 mole of the ions, and we have the diffusivity divided by RT. So we just introduced this equation without any explanation, but we are going to explain this equation in the next class. So let's accept this equation is true, for example. So this provides a relation between the drift speed and the force experienced by 1 mole of ion. So here it is basically electrostatic force per mole of ions. So it is the charge carried by 1 mole of the ion multiplied by electric field. So it should be the force. And this 1 mole of the charge carried by 1 mole of ion should be a product of Z and F. F, you know, F is 96485 coulomb per mole value. So if you substitute large Fm here, then now we have the relation between the ionic mobility and the diffusivity like this. So this relation is called Einstein relation. So let's play with this equation based on this example. So the mobility of one lithium cation is given like this, and temperature is also given. It's a liquid water solution, and it was asked that we're going to find the ionic diffusivity of this lithium cation based on this given mobility. So if you use the Einstein relation, then we can simply find out the ionic diffusivity, and you simply put all the parameters given here, and you can find out its value should be 1.03 multiplied by 10 to the minus 9 square meter per second. So the Einstein relation directly relates the diffusivity ion with the ionic mobility. Okay, so basically the mobility is proportional to the ionic diffusivity according to this Einstein relation. If the diffusivity is very high, then the solid ions should be very mobile. But one thing that you should be very careful is that the mobility does not decrease as the temperature raises. D is a function of time, which increases more rapidly than the temperature itself. So next topic, let's think about the relation between the limiting molar ionic conductivity, small lambda, to the ionic diffusivity. So we have derived the relation between the lambda and U is a lambda equals to Z U large F, and you substitute this Einstein relation, then you can find out the relation between this um, limiting molecular ionic conductivity and the ionic diffusivity like this. Everything is just proportional one another. So we can use the law of the independent migration of ions, and we're going to combine this with this equation having the Einstein relation. Then you can express the limiting ionic conductivity large lambda m as the sum of these two factors contributed by the cation and anion respectively, and you can find out this relation. So relation between the limiting ion conductivity and the ionic diffusivity of the cation and anion. So this relation is called Nernst-Einstein equation because as this equation is derived by the Nernst based on the Einstein relation. All right, so that's pretty much everything for today's course, and we have talked about the viscosity and the ionic movement under the electrostatic field in the liquid phase. So we have discussed the relation between the viscosity and the temperature, and we discussed of the Coulomb law, which is only true when the electrolyte is strong electrolyte and the concentration is very low, and also discussed about the law of independent migration of ions, and also discussed about the relation between the drip speed and the electrostatic field, which basically explains the size of the drip speed under the force equilibrium between the viscous drag force and the electrostatic force. So also discuss about the relation between the ionic mobility to the size of the hydration sphere of the ions. And then also we combine the Einstein relation to get this law of independent migration in terms of the ionic mobility, and also drive the relation between the diffusivity and the ionic mobility and the limiting ionic conductivity. So that's pretty much everything for the electrolyte physics, and we're going to talk about liquid phase a little bit more, but we are going to focus on the diffusion instead of the movement of the ions under the electric field. So we're going to talk about the diffusion from we focus investigate the diffusion from the thermodynamic viewpoints, and also we're going to drive some diffusion equations next class. So thank you for listening to this lecture, and see you in the class, and happy holidays.